Okay, so as I just said, let's just start with um, regular contents, and then afterwards we can start talk about possibility. I mean, the project and some other logistics as well. Um, hold on, let me open the file. Okay, so now you can see my screen, right? See the slides. Yes, good. So this week we're talking about game theory. So as you can see that we have touched upon a couple of different subjects already, including earlier we have just simply to use difference to do a math model, and then we studied linear programming, studied linear regression, studied simulation, and also studied um, studied decision trees. And then this week we're talking about game theory, and then what we're going to talk about is an introduction followed by a total conflict game, and then total conflict as a linear program. How can we model a total conflict game as a linear program? And then talk about decision theory revisited, games against nature, and alternative methods for determining pure strategy solutions, and followed by alternative shortcut solution method, partial conflict games, which is a little bit more complicated than total conflict games, and with illustrative modeling example. So hopefully, I'm not sure if any of you already had some exposure on this, but let's say what's the difference here. So earlier last week, we studied decision theory, studied about how to model a problem using decision node and probability node to using expected value of a specific path or the decision for a specific decision node, and then we can evaluate possibility options, different options, and think about which one would be the best approach. And then here, as you can see that decision theory is really just one player, but for game theory, it's two or more players. And then in our particular examples, majority of the time, we're only talking about two-player game theory, and then more players would be even more complicated. And then for game theory, it has two types. One type is called total conflict game, and then the other type is called partial conflict game. And then for total conflict game, there is something called pure strategy solution and mixed strategies. And then a pure strategy is a course of action available to a player. The strategies chosen by each player lead to outcomes with payoff for each player. So hopefully you realize that game theory is something that was developed by John Nash, who actually won the Nobel Prize because of this specific pure strategy solution as his dissertation when he was at Princeton. And then let's see what is it, what exactly it is. A strategy A dominates a strategy B if every outcome in A is at least as good as corresponding outcome in B, and at least one outcome in A is strictly better than a corresponding outcome in B. So dominance principle, a rational player should never play a dominated strategy in a total conflict game. So a Nash equilibrium is an outcome where neither player can benefit by departing unitarily from its strategy associated with that outcome. So let's say what's specifically, let's say if we have an example, and then we can discuss what exactly that means. And then some more definition. If for each possible outcome, the payoff for each player sums to the same constant, 100% in our example, the game is classified as total conflict. The arrows that we just showed apparently is not showed. It's next page actually. And then let's take a look at the next page. And then let's actually, before we look at the next page, let's take a look at this definition first. For any game, we draw a vertical arrow from the smaller to the largest row value in each column, and we draw a horizontal arrow for the smaller to the largest column value in each row. When all arrows point to a value, we have a pure strategy, Nash equilibrium. And where is the example? Looks like I missed some slides here in this particular version. Yeah, hopefully I can come back and find it. Hold on. Let me take a little bit time and try to find it. I apologize that at the moment I really cannot find that example that for yeah, I think I was probably referring to a specific example in the textbook, but it's a little bit troublesome for me to go to the textbook. In any case, we probably should go there. Otherwise, you wouldn't be able to understand what I'm talking. So let me hold on. Let me try to find the textbook, and then we can continue with this subject. Give me 1 minute, around 1 minute. Yes, but the thing is, I need to figure out exactly where I'm talking about that particular example. So, do you have any questions meanwhile while I'm trying to figure out the specific example? Any questions regarding the um, project? It could be, but the thing is, I don't have the textbook. I mean, I don't have the textbook readily available. I have to log into the system to find it. Okay, now it's better. So let me find here. Okay, so here is the example that I was going through. Somehow that page was apparently lost in the slides. So basically, let's take a look at this example. So for hardware store such as Home Depot is making, let's go back to the previous page. So here it says, suppose that large city is located near small city. Now suppose a local neighborhood hardware chain such as Ace will locate a franchise in either large city or small city. Further, a mega hardware store franchise such as Home Depot is making the same decision. So it will be located either in a large city or small city. And each store has a competitive advantage. Ace offers a smaller store with perhaps a convenient location, whereas Home Depot has a much larger inventory. So analysts have estimated the market share as follows. And then says that so Ace, that is to say both Ace and Home Depot located in the same city, large or small, Home Depot will get 60% of the market. And then if Home Depot is in the large city while Ace is in a small city, Home Depot will get 68% of the market share. And then on the other end, Home Depot, but if Home Depot locates in a small city where Ace is in a large city, which is bottom left of the matrix, which is 50% of the Home Depot will get only 52% of the market. On the other end, if both of them are in a small city, both of them get 60% of the Home Depot will get 60% of the market share. So as you can see that this particular matrix is really explaining the Home Depot market share, given that for different decisions that Home Depot and Ace are going to make. And then if we look at horizontally, apparently for Home Depot, it would like to move to a more they definitely want to be in a location that have more market share, right? So in that case, if we look at the first column, no matter what, Home Depot will choose large city, because if it choose small city, and then if Ace choose large city, then it'll have less market share, right? So in that case, it would definitely choose large city from the first column. And looking at the second column, we would see that for Home Depot, it's definitely beneficial for itself to choose large city as well, by comparing those two numbers, 60 versus 68%. So in this particular case, we know that Home Depot should choose large city. And then let's think about Ace on the other end, which would be illustrated in the next page. And then the correspondence table for Ace is as follows. Because as we know that in this particular cell, first cell on the upper left of the matrix, if this matrix is for Home Depot, correspondingly for Ace, for the upper left corner, it should be 40% and 32% for the second cell. So this is really the matrix for Ace. And then now let's look at the decision that for Ace to make. For Ace, it should choose, looking at the horizontal, it should choose from 32 to 40. So in other words, it should choose large city for sure. It doesn't want to choose small city, right? So if by looking at these two matrices together, the next matrix that we can see that no matter what, for both of the Home Depot and Ace, both of them should choose large city. And then note that outcome, large city, all arrows point into that point, and no arrow exits that outcome. This indicates that neither player can unilaterally improve a stable situation that we refer to as a Nash equilibrium. So this is an idea as simple as that. It's the Nash equilibrium. So, and then if we go back to the slides that we just went through, it essentially says for any game, draw a vertical arrow from the smaller to the largest row value in each column, and we draw a horizontal arrow from smaller to the larger column value in each row. When all arrow point to a value, we have a pure strategy Nash equilibrium. So in this particular case, if we do that for two steps. First step is do the smaller to the bigger for the columns, and then do the second thing for each row. You do smaller to the bigger. Use the arrow to point from smaller value to the bigger value, and then we find that there is a point that indicates that neither of the player can unilaterally improve a stable situation referred to as Nash equilibrium. So that's the definition of Nash equilibrium. So let's continue with this. Yep, that's that. And then if we continue with this. And then as we say, okay, just now we talked about pure strategies, and then we would talk about mixed strategies as well. For partial conflict games, it would without communication, with communication, and with attribution. Let's talk about how to model a game to a linear program. And then we actually have to go through the example that we just had. Hold on, where is it? Okay, it's right here. So if we continue with, there's another example. It happened that next example is modeled as a yeah, this one. Let's look at a different example that is a duel between a pitcher and batter. This particular example, I believe it had some discussion earlier in the textbook. So in a game of baseball, a pitcher attempts to outwit the batter against a certain batter. His best strategy may be to throw all fastballs, while against a different batter, he might be better off throwing all curveballs. So finally, against the third batter, his best strategy might be to mix fastballs and curves in some random fashion. But what is the optimal mixed against each batter? So let's think about this particular example. As you can see that if we have this matrix for I think it's a batter's we can call it as response matrix. So it may not be, yeah, let's for now, let's just use this word. So if a batter can anticipates the pitcher is throwing a fastball, he will either hit 0.4 or 0.2 depending on whether the pitcher throws fast or curve. If he guesses curve, he will either hit 0.1 or 0.3. So if we continue with the strategy that we just discussed, we just horizontally and vertically we try to draw the lines, and we can see that apparently this example would be 0.4 would be the Nash equilibrium, right? So in this particular example, because this one, the top arrow is not pointing all towards 0.4, right? So there is no Nash equilibrium in this case, right? There is a arrow that's exit this 0.4. So in this case, a player can always improve by unilaterally changing strategies. But what is the optimal mix for the batter and for the pitcher? So that it would be a mixed strategy. And then the textbook actually continued to talk about some examples for the partial talked about a partial conflict game, and then you probably need to take a look at this example afterwards, because here I don't have time to continue with this particular discussion. I want to move on to the linear program model. So continue with this example, and then we must now solve for the optimal matrix of strategies with which each player should play each strategy. First, let's view the game tree. So that's to say that if pitcher gives a fastball and the batter, if batter also can guess that correctly that it's a fastball, then it will have a payoff. This matrix is called you can also call it payoff matrix. It is 0.4, right? And then if it guessed incorrectly, and then he get think it's a curveball, then the payoff is 0.1. And correspondingly, we can have this branch, the bottom half of the branch of the game tree as well. And then note that computing the batting average is the expected value if we know the probabilities with which each player plays his two strategies, right? For example, if the pitcher mixes the fast and curve with an equal probability, a half, in that case, we can see that, and then correspondingly, and the better uses the mix strategy, 3/4 fast and 1/4 curve. I apologize. This is not guessing. It's really just how the batter actually respond with the pitcher's fastball, slow ball, a curveball. And then in that case, we can see that the batting average would be 3/8 for this branch, and then 1/8 for this, and 3/8 and the third branch, and 1/8 for the last branch. Just because that it's a half times 3/4 for the first branch, right? And then the batting average is 0.275, just because of this payoff times the probability expected value for the batters, so that we can get the batting average to be 0.275. And then now the question is, how can we model this particular example as the batter's decision as a linear program? So first, let's consider that the batter's decision, he wants to choose a mix of guessing, fast, and curve to maximize the batting average. Let's define our variables as the following. So A is the batting average, and X is the portion of the batter to guess fast, and then Y minus X would be a portion of for the batter to guess curve. So the objective function is really we're trying to maximize this A, which is the batting average. And then what's the constraint? The constraint is really that let's go here. Let's take a look at the model here. The constraint is that if pitcher is using a fast strategy, in any case, the batter's decision payoff being that X portion of batter guess fast, X times the payoff, which is 0.4, plus 0.1 times Y minus X would be larger than or equal to the A. So A is less than that, and then so that we can maximize that A. And then correspondingly, if pitcher is using curve strategy, we would have A less than or equal to that. And then we know that because X is a proportion, it would be between 0 and 1. And then we can say that based on what we studied last 2 weeks earlier, we can try to find the feasible region and try to solve this maximized A, right? And then we can see that the optimal solution really occurs when X equal to 0.5 and A becomes 0.25, which is it happened that the same as what we just saw earlier as that game tree illustrated in the game tree. And then we can do some sort of sensitivity analysis to see that what if the payoff changes, and what would be the strategy that would be appropriate. And then as we discussed, for the linear programming, we can also solve the batter's decision, solving the linear program algebraically, essentially trying to use all the extreme points and see which one is the best, which have the highest payoff. And then if we look in a different perspective, how can we use what's the pitcher's decision? And then correspondingly, we set up this linear program to represent the pitcher's decision. And then apparently the strategy would be complementary to the batter's decision. And then optimal solution occurs when y equal to 0.25 and a is also 0.25. And you can do some sensitivity analysis, and then you can similarly use algebraically to solve the problem to find the optimal solution for the pitcher's decision. Yes, so let's go to page 401 to look at some geometrical interpretation of the solution. So let's say, the textbook further discuss that if we consider the batter's decision and the pitcher's decision simultaneously, we have the game tree showing the figure 1020, which is right here. And then it essentially says that, okay, if pitcher do fast, X probability, curve 1 minus X probability, and then batter's decision would be Y fast and 1 minus Y curve, and then payoff is 0.4, and the probability of that is X times Y, and then for each branch has corresponding probabilities. And then the expected value for A is really just this formula, and where X is a proportion with which the batter guesses fast and Y is a proportion of the pitcher throws fast. Allowing X to vary in increments of 0.05 from 0 to 1 so that we can see some overall payoff matrix. Let's see, go to the next page. So essentially, this is the expected values for the batter and pitcher duo at 0.05 increments. And then we can see based on this example that X should be choosing 0.5 while Y should be choosing 0.25 so that the payoff is 0.25, which is optimal for both of them. So let me see what's next that we can discuss. Okay, that's that. And then textbook also continued to discuss that decision tree for a firm's decision, whether the economy is good or it's bad, and then manufacturer should be think about smaller or large manufacturers, and with the corresponding payoff. And it's very similar, actually. It's almost exactly the same as what we just discussed for the linear program for the firm's decision and the optimal solution for the firm. Correspondingly, a linear program for the economy decision. And then we can find the optimal solution there. And then, so basically those two are pretty much the same. And then also, the textbook has a example on the investment strategy example, and it's on the textbook page 413. Definitely review that example yourself. And it's very similar to the firm versus economy game, which is also similar to the batter and pitcher game. And then there's another methodology to see how we can use are there any other methods to talk about determining pure strategy solutions. So when the maximum and the minimum values are the same, the resulting outcome is called a saddle point. So if a game has a saddle point, which is for the first example that we discussed, which is a 60% for Home Depot and for Ace. Then that particular point is called a saddle point. It gives the value of the game. Players can guarantee at least this value by choosing their max min and min max strategies. And then let's see. So min max strategy is let's go to the textbook. So min-max method is saying this, right? So we're saying that we choose the minimum value for each row and then choose the largest or maximum of those minimum to determine a maximum min value. So let's look at choose the minimum value in each row. In this first row, the minimum is 60, and second row, the minimum is 52. And then choose and then we choose max of those two minimum, which is 60. So in that case, 60 is the saddle point or Nash equilibrium. And then correspondingly, we can use max min strategy. And then what is min max strategy? So let's go to what is the min max strategy. So for each column, look at the minimum first. Look at the maximum first, and then look at the a minimum of those two values, which is 60 as well. So in this case, it arrives to the same conclusion as what the way that we tried to go through earlier. So this particular strategy, this particular method is called maxim min and min max method. And then as a minimax in min-max and max-min for this particular for the example for pattern picture are different. In that case, we know it's not a pure strategy saddle point because there's a way to move away from the equilibrium. But for this example, for the example for Home Depot and Ace, it is a saddle point. And Prison's Dilemma is has an example there talked about the it's a very classic example in economics and also in many of the game theory. Game theory is part of economics, just to be more more precisely speaking. It is part of economics. So. And then because we didn't really talk too much in here about this example, hopefully you would go through that. But the basic idea is the same, just payoff becomes two value. In other words, for country A would be the first element of this 3-3, and for country B would be the second element of that 3-3. So correspondingly for the 1-4, 1 would be represents the payoff for country A, and 4 would be the payoff for country B if country A choose this arm and country B choose arm. So in this example, we find that 2-2 is really the strategy. In other words, both of the countries would arm instead of disarm. Yeah, this is without communication. This one, yeah, we didn't discuss too much either, but it's similar to what we have, even though based on this payoff matrix, it is different strategy. I mean, they have different, there is no Nash equilibrium, there is no saddle point. And then there is something we call that for two-player game, there is something called partial, the chicken game, which is partial conflict game, but it does have a communication. If they talk to each other, and then what would be the best point that they would be chosen for each one of them. So here, yeah, I'm not going to go through too much of detail, but I think it's definitely worthwhile for you to take a look at these two, a couple of slides, 130, I mean, 10.6, these three examples in 10.6. It's worthwhile to understand them, even though it's probably sufficient for you to understand the pure strategy, mixed strategy, and also the linear programming formulation for total conflict games. But for partial conflict games, it's definitely worthwhile to take a look. And some modeling example, but this modeling example is really more broader application that you can take a look. Hopefully they will guide you through for your future usage when you think it might be useful. And then this is the homework for this chapter. Okay, this is homework, but you only need to choose 3. Yes, so let me move on to next topic, which would be for next week. And then we're switching gears to something else. So as you can see that looks like it's different modeling methodology that we just discussed, game theory. And last week we discussed decision tree. And the week before we discussed linear programming. Looks like they're somewhat different, but apparently they are interconnected, right? And but however, what we're moving towards is really a bit more different from what we just studied in the previous 3 weeks. So Seka has a question that can more than one outcomes be in Nash equilibrium? My answer would be no, even though I'm not 100% sure. But let me do some search, and then hopefully next week I will be able to answer that question better. So let's continue with the modeling with differential equations, and we're going to have discussion on population growth, prescribing drop dosage, breaking distance revisited, graphical solutions for autonomous differential equations, and numerical approximation method, separation of variables, and the linear equations. So for difference equation, we know is delta p is p at time t plus delta t minus pt can be represented as k times p delta t. And then if we take a limit of that delta p divided by delta t with delta t approaching 0, then we can see that that's a definition of difference, right? Different derivatives of p in terms of t, and then dp divided by, dp over dt equals to kp in this case. And then we know that this derivative is really the rate of change. So if assuming that in this graph that we know that if delta s and delta t is very small, then it's really just slope of the specific point that's under discussion. And then, as I just said, the derivative as a slope of the tangent line. So as long as our interval is small enough so that this tangent line has it is the derivative. And then for population growth, if we say that there is a certain probability, there is for the population in the time t plus delta t is based on the population of time t, and also there is certain growth. Meanwhile, there is certain death rate that so that we can model this problem as this particular relationship. It looks straightforward, right? And then let's take a look at how can we further represent is as differential equations. So we can say that if we use and then if we move pt to the left hand side, we know that on the left hand side it would be delta p. So and then if we divide it by delta t on both sides, we say that delta p over delta t equals to b times p minus c times p. If because b and c both are constant rate, b minus c can be represented as k. And then in this case, if we take if we take a log on both sides, yeah, I'm having the difficulty to understand what this means here. Let me say okay, so we say that dp over dt equals to k times p, and then we can separate those two variables. Yes, that's how you solve this differential equation, right? So you use dp divided by p and use k dt on the right hand side. So in that case, if we integrate of both sides, we can get ln p equals to kt plus c. Hopefully you still remember this, because ln p derivative would be 1 over p times dp. So in that case, if we integrate on both sides, we should get this particular equation. There is a constant that's added there because derivative of constant equals 0. If we reverse from 11.6 to the previous equation that we saw here, we can use the derivative. So integration correspondingly will go back to equation 11.6, right? And then apparently we don't know what this constant is, and then hopefully we would be able to solve it, and then we'll let you know that how we solve it. Applying the condition of t0 equal to p0 to equation 11.6, we would be able to find out c. In other words, there are certain initial conditions that we actually know, and then in that case we can find out c, so that equation 11.6 becomes ln p equals to kt plus ln p0 minus kt0. That's the population growth model. And then simplifying algebraically, what we did here is we divided by ln p0 to the right hand side. We minus ln p0. We moved ln p0 to the left hand side, or in other words, we minus ln p0 on both sides, so that on the left hand side it becomes ln p minus ln p0, which is ln p over p0, and on the right hand side it is k times t minus t0. And then we say that, and then if we take an exponential of this function, we can say that pt is really a function of p0 times e powered by k times t minus t0, right? So this particular function is known as Malthus's model of population growth predicts that population grows exponentially with time. So this is great. That's an example that we have. And then, of course, I mean, the textbook has some further examples there to discuss how you can actually verify that model. But this is the whole process from the initial formulation all the way, based on the initial condition, all the way to the end of the solution pt equals p0 times e powered by k times t minus t0. And then if we see that whether we can refine the model with limited growth, that assume that proportionally factor k is now no longer constant, but the rate of population growth, and there's a certain upper limit, which is the m of the growth, which is so that we can use k equal to r times m minus p to define. And if we continue with similar methodology to separate the variables and then try to do the integration, you can see that at the end, pt is defined equal to m times p0 divided by p0, etc. That's population growth model with limited growth. And then a different example here, prescribing drug dosage. How can the doses and the time between doses be adjusted to maintain a safe but effective concentration of the drug in the blood? And also there's an example regarding braking distance revisited and graphical solutions for autonomous differential equations. Really what you really need to do to understand would be the 11.1 and 11.2. One is the example that we just discussed. Second example would be this drug dosage. They are actually very similar. Yeah, this is just saying that earlier we have using, I believe that was difference method to model the braking distance. Just worthwhile to point out that using a different methodology will result in the same solution as what we discussed earlier in the textbook, which is worthwhile to go through. And then graphical solutions of autonomous differential equations to see whether there's some sort of convergence there. You really need to read the textbook in this section as well to understand it, even though it's not as important. And then for the numerical approximation, so this part actually is worthwhile to spend a little bit more time. That is to say that how can we, especially how this particular approximation, which is called Euler approximation, how do we use Euler approximation to approximate the true solution curve? And then the idea is using a tx equal to y0 plus g x0 y0 being an initial condition, and then use x minus x0 being the distance between the specific approximation that we are trying to evaluate as the x-axis difference, and then try to evaluate the corresponding y value. In other words, using the tangent line to approximate the next point, which is the difference delta x, which is xy minus x0, and then use the function form times delta x plus y0 to get the corresponding y1. That's the idea here. And then separation of variables. as you realize earlier, we discussed dp divided by p, and then move everything on the right hand move the rest of stuff on to the right hand side. That is called separation of variables. So that we know this is really part of calculus. That's why it's important. Remember that at the beginning of the semester, I asked you guys to review the appendix. I believe it's appendix A. So if you haven't done that yet, and then if you realize that you are having some difficulty to understand this particular chapter, you should read appendix A again so that you can link them together and try to understand why this particular approach to move things to the left, to the right, and then to solve the problem itself. And this is the same thing as how can we separation of variables and use integration technique to find the corresponding solution. Yes, it's still the same thing. Discuss the uniqueness and the existence of the solution. Okay, this is the test homework for this section, chapter 11. Hopefully you would have time to review the bulk of the material in the textbook so that you have a much better understanding. Other than this, you have any questions for the two chapters? Okay, if not, I just want to discuss a little bit about our plan. So as I said, that I actually set up a sign-up sheet on the website, and looks like hold on. Looks like even though some of you actually sent me an email, and the majority of you looks like working as an individual team. Not sure if some of you actually already teamed up, but you just didn't put it in here yet. Some of these questions I didn't get a chance actually to review yet. So basically, look like a lot of you guys are working just by yourself. And then if you could, what I would do is I'll just summarize those information. I would say, for example, I will just reply and say, okay, team 1 is Jeffrey by himself, and team 2 would be Seka with just by himself, and then something like that, so that we have a complete list regarding all the teams, and then we can plan ahead regarding what to do for the final presentation, etc. And next, let's quickly take a look at look at the syllabus. So what's the plan? Okay, this week is week 9, and we have homework 9, and next week we'll have homework 10. Okay, that's what I am looking. For project proposal draft, you should be submitting by end of this week. It is draft just because that I want to discuss with each of you guys after you submit the draft, so that you can finalize your proposal by week 11, which would be the week after next. And then, so as I just said, please submit the project proposal, and then we start discussing in the next 2 weeks. And then after that is finalized, you would have from week 12 all the way to week 15, which is 12, 13, 14, 15, 4 weeks to finish the project. So Sanya was asking if you can have 3 people on the team. Yes, you can have 3 people on the team. So if you have 2 people, you just think about 2 questions, 2 problems, or even 1. I really don't, I'm not called upon if you have 3 people, you're working on 1 problem. I'm okay with that. So in other words, if you only have 1 problem to solve, if you think about alternative solutions, even just 2 solutions, that would be sufficient. So in general, I encourage you guys to work on some problem that's not from the textbook, but it's definitely fine to select some of the questions from the textbook as I prescribed in the project requirement there. So there's no issue if you choose option 1 or option 2, but apparently option 2 would be better in my opinion. But it doesn't hurt your grade if you choose option 1. And another thing is I encourage you for a team collaboration. If you can team up with someone, definitely try to do that. I also understand if you because of the timing, because your work schedule, etc., you have to work by yourself. It's perfectly fine as well. Yes, and the textbook has some math computation challenges as well. It would be interesting as well. In terms of the application aspect, it's probably not as interesting, but in terms of the intellectual curiosity and intellectual depth, is definitely something that's worthwhile to continue exploring if you are interested in some of the math computation challenges and the projects from the end of the chapter. Yeah, some of them are really complex. Okay, so this is everything that I prepared. Actually, initially I was planning to discuss homework 7 as well. Probably we don't have time. Let's do this. Next week, let's discuss for the office hours. We can discuss homework 7 and homework 8. I haven't finished grading on homework 8, but I will do that by mid of next week so that we can go through 7 and 8. And I also still have the Markov chain and dual problem on my plate that I plan to discuss. Hopefully next week we can discuss one of those 2 topics as well. So I'll send you guys an email so that you know what I'm going to cover, and then in case you're interested, definitely try to join us. Okay. That's pretty much that I planned for today. Anything else from your end? If not, we'll just stop here, and you all have a good week. Hope to see you next Wednesday in the office hour. Thank you.